Well, as an improvement to consider the carrying capacity, there's another guy, his name is Verhulst Pearl, proposed a different model. And you still have the change rate of the population related with the population itself, but after some point, it's also related between the difference of the carrying capacity and the population. So intuitively, look, if the C is the carrying capacity, if P is less than C, fine, then the C minus P is positive. Then you still got the positive times the positive, and then the derivative is going to be positive. If the derivative is positive, you know the population still grow. However, once you grow to a stage and the C minus P equals 0, then your right hand equals 0. What does that mean? The derivative equals 0 means you flat out. You're not going to grow. In the worst case, like this bunnies in this flow, they run out of food, and then the C is big, the P, what I'm saying? I'm saying the C is bigger than P in the first place, C bigger than P. If now the C is less than P, the population is greater than the carrying capacity, we really get trouble. And then now the C minus P is negative, and then the right hand is negative. You find that the derivative is negative. What means derivative negative? You got a decreasing, right? So that's kind of intuitive explanation of the model. I think it should make sense. Again, this is a separable equation. I can put all the P on the left hand, put all the T on the right hand, then do the integral. I'm not going to go to that detail and let you read this solution. All you need is a calculus 2. Maybe you get a C is enough. Once you solve this, what you get is this equation. A little more complicated than the exponential function. And the first question is, how do I know it makes sense? Well, you can check 2 points at least. When the t equals 0, and then e to the rt equals 0, and then this is going to be 0 here, 1, and e to the 0 is 1. Then you get a p0 plus c minus p0 over cp0. Look, you take away this p0, cancel out the c, and then you get the p0. That's the first checkpoint. Another checkpoint, pay attention. When t goes to infinity, look, e to the negative t, this term, take a limit, is going to be 0. That's decaying here. And then you get the cp0 on the numerator. Divide by p0, cancel out the p0, you get the exact c. So that's the point. When t goes to infinity, you got to the carrying capacity. That means you're not going to increase any more. So if you draw a curve, it's really this curve called the logistic curve, and the model sometimes is also called the logistic model. So you get the asymptote here. You bet this line is precise that P equals C, which is the carrying capacity. And you maybe start from P0 here. That's your original population. That's when T equals 0. And also, of course, is not real. So such a curve, sometimes they call it S curve, but the mathematician called it logistic curve. It's a phenomenon. Give you an example. Your learning curve, most probably, is a logistic curve. You find in the beginning you have very hard time to get anything. You did not learn anything after half a semester, and when you push, you suddenly cross this threshold. You learned a lot, and then after you pretty much got an A or B, and you find that you cannot learn quicker as it used to be. Oh, the learning curve is like that too. So for a good student, you always have to know when you push through this and get to here, then you might now invest your time to other subject. So this makes more sense, right? The population, if you look at the world, the population prediction, and you understand this yellow curve pretty much like a logistic curve. And the red curve is like the Malthusian curve. The green curve is the permissive phenomena, maybe a natural disaster, another war, like the North Korea, who knows. But what is the carrying capacity? That's a question for, let's say, the world population. Now we got 8 billion people. Somewhere are struggling for survive. Somewhere are still prosperous. So what is the carrying capacity? Somebody may argue, could be 16 billion. Somebody maybe say, hey, it's more than that. It could be 40 billion because of the science. But nobody knows. That's an hyperbolic. It's a hypothesis. You don't know. And that's the major criticism for the carrying capacity model. The problem is this. The carrying capacity take a top-down approach and start to assume something called the carrying capacity they don't know. But we do know it exists. Another approach, I will call it computation model, start from bottom-up approach. If you consider how much potential this world population can increase, but you start to look bottom up for how hard it is to survive, to find a job, to get enough food, how much you have to compete for one surviving food supply. So if you look at all those statistics, look at the computation level, intensity, you get the kind of feeling how close we are to the carrying capacity. So the new model start to observe the probability of 2 random selected individuals, could be human, could be robots, to compete for one share of surviving food. That means if the failed individual could not get it, of course, then it die off. So it's a modification from the Malthusian model. Here's the Malthusian model. But you subtract the failure of the computation, and we get the artificial constant B. What this B stands for is the computation factor, is the probability. You know, you not always have to compete for survive, but if too many people, you definitely will compete for a job, for feed the family. That's true everywhere. Thanks for the welfare system so far. And then this is a probability. And then what about this 1/2 of p, p minus 1? Well, that's the combination choosing 2 from p people or population. Now, give you a simple thing. P equals 3, and then A, B, C, you got the 3 different choices. A compete with B, B with C, C with A, then you have 3 times 3 minus 1 over 2, which equals 3. But if you get the 4, D, you add to another 3. then your P equal 4 is 4, 3 minus 1 over 2 equals 6. And you get a 5, you're going to add more. So that number here is the combination of 2 compete for 1 share of surviving food. So the failure die, then you cancel out this death rate due to failing the computation. And that's, again, a separable equation. Well, if we just look at this equation and compare to the carrying capacity model, different philosophy. One is top down, one is bottom up. Different representation, but I will leave this for you to prove. In mathematics term, they are exactly the same. Now, the hint is this. If you rewrite this, this is a quadratic equation for P. And if you rewrite the second one, you get this. And the plus K plus half B of P, again a quadratic of the population. So they're really the same model. You can match one by one. In a term, you use the B and the K, you can find the C and the, what I call that, R. And use R and the C, you can reverse to find the B and the K. So in this way, I can start to think about the carrying capacity from the statistical point of view, from the macro level. That is how you do the research. And if you cannot observe one way, observe another way. And always start from what you can monitor and observe. I leave as an exercise, I have this MS Excel file with a very nice simulation, and you can simulate and find that this is also a logistic curve like that. Well, let me watch my time. Very good. I have another half hour.